Well, good morning, everyone. So it was about the year 2000 or so that at Arcadis we started looking very closely at the geology of our sites because we were having trouble making our remedies work. We were putting in small volumes and expecting them to spread out on their own of our injected reagents, that is, small volumes of the injected reagents, hoping that they would spread on their own because we were fully bought into dispersivity. And so it started a series of changes, a series of adaptations that we went through that in 2008 we really culminated with the publication of what we knew at that point in remediation hydraulics. So we've had a little more than 10 years of experience looking closely at the geology and how it interacts with our remedies. And at least 10 years now where we've been pretty full on with what today we would call remediation hydrogeology, or for us, remediation hydraulics. And I want you to think about this, this small section. This happens to come where I have a cottage, Beaver Island, a gravel pit. But this calls attention to one of the issues that we're starting to tackle now with the second edition, which Jeremy mentioned we're trying to get through. We're late. But it's the issue of sorting. And how would we detect a formation like this with our classic geology tools? We've got some pea stone here that's very well sorted, very clean, and this is, in this section, this is where 99% of the flow is going to go. We've got some moderately permeable sands here, and then we've got these stones, which, if you think about it, wow, those are big stones, they must be highly conductive, but what you really have is medium sand with 80% blockage. So it's actually the lowest permeability section of that profile. So how do we detect this? And we need to realize that variation like this, more subtle variation in sorting in sandy aquifers, can generate concentrations of flow that affect where our contaminants are transporting, where our injected reagents need to go, perhaps. We're not really there yet in applying the tools that we have to be able to detect situations like this that are not always as obvious, but they're embedded in almost all of our aquifers. So the remediation hydrogeology, it's an interdisciplinary practice, and our objectives are in terms of quantifying and removing unacceptable contaminants from the groundwater. So we've got some responsibilities that we need to execute. One of them is we need to be able to map our contaminant distributions and transport, and Rick was giving us a good foundation in the previous talk. We need to quantify the potential contaminant exposure based on the current situation and based on the future, if it's unattended or even if we put remedies in place. And we need to design control strategies and remedial actions that will contain or eliminate the potential risks associated with the contaminants in the groundwater. That's a pretty tall order, and we've got many new tools today. I'm very optimistic that we have the ability to do this. And I personally, I'm not bought into the TI argument. I think that technical impracticability, there's the other TI that's the real one, and that's the technical incompetence. And that's the TI that we need to defeat. There will be some sites that are very awfully difficult and perhaps impractical, but we need to shake out the inability to properly quantify our distributions and transport before we declare true TI. So why change was 10 and 15 years ago, why it was needed and still is. We're having difficulty predicting contaminant migration, and the remedies are often disappointing us. Cost of closures are high, and the past experience is leading a very active movement that Jim was talking about earlier to declare sites either as complex or technically impractical. So the water supply legacy, Rick talked about this earlier, and there's nothing wrong with water supply hydraulics. And when you think about it from the perspective of a water supply engineer, they need to systematically understate the capacity of the aquifer, right? If they build a production well or a production well field, they need to be sure that it can deliver more than what the needs of the town are. So water supply hydraulics and the modeling that supports it, including ModFlow, systematically understate the productivity and transport velocities in aquifers. So the problem to be conservative for water supply is the exact opposite of being conservative for remedial work and for contaminant tracking. Because if we take a model that is understating productivity and transport of the aquifers, we're going to understate transport processes ourselves. So we have to be very cautious. The bulk analysis of aquifers, that's the foundation of ModFlow, and a lot of the remediation hydrogeology of the 1970s, 80s, and 90s was really a bulk analysis, and it's an underestimate, and a lot of our problems are rooted in those foundations. So there were 4 simplifying assumptions that I distill all of that down to. One is that the aquifer is homogeneous. Secondly, that it's isotropic. Thirdly, that it's Gaussian, that fluid movement or, dissolved constituents in the fluid are moving in a Gaussian fashion, and that the aquifer is at steady state. Of course, none of those actually happen at our contaminant sites. So we need to outgrow those assumptions. So the revised conceptual framework, and this is what we started to put into remediation hydraulics, is that we should expect aquifers to be heterogeneous and anisotropic. We should assume that's the rule, and I think Rick showed us very well why that should be the rule. It's built into the aquifer by the depositional processes themselves. So the problem, though, becomes solvable, tractable, with some intensified well-designed characterization and the hydrostratigraphic analysis to tell us what how the formation was structured so we know what to expect. It can educate our characterization process, and we'll be much happier with our outcomes. And I wonder how, with conventional tools, how could we ever characterize a formation like this? Even knowing that this is in Alaska, by the way, it's not a contaminated aquifer. But even if we know that that's how it's structured, it's going to be difficult to investigate, but we need to know what to expect. What behaviors should we be expecting so that we know how to search for them? So if we abandon the simplifying assumptions, what can we gain? First, we're going to get improved predictability. Modeling those is going to be a more difficult challenge, and we're working on this right now. We're finding that we can get improvements if we use ModFlow, the engine, at a very highly resolved application rate, but there's some problems with the solvers. There's some inconsistency from one solver to the next. So we think all has not yet been settled in the modeling world, but very definitely we need to be moving into more highly resolved models. We need to look at the full 9-element tensor, not just simplify it down to isotropic. There's a lot of mathematical discussion that I can't have with you, but Scott Potter and Joe Quinnen could. But there's huge need for improvement in the area of the models themselves. Remedies, once we define the pathways, what we're finding is that the remedies can be much more focused. Because as a rule of thumb, 90% of the contaminant transport is occurring in 10% or less of the cross-section. So it allows, once we locate it, we can go hit it and hit it hard, but we have to locate it first. So you have to admit that your aquifer is not isotropic homogeneous, go search for the transport pathways, and once you find them, you can be very cost-effective. So the remedy effectiveness can increase significantly if we abandon the old assumptions and take on the new. But it does require some increased investment, perhaps, on the characterization side. The payback, though, is very good. So we want to, how can we use that data to reduce remedy costs? By focusing the remedy and treating only the part of the aquifer that needs it. And it can be a very, very large reduction, reduced down to 10 or 20% of the level of effort. So what we're going to do, we're going to revise the conceptual foundation, and it has to really precede the conceptual site model development, get rid of the homogeneous isotropic mantra, rotate into the heterogeneous anisotropic, log normal, not Gaussian, perpetual transient state, not steady state, and we'll all be happier with our outcomes. One of the things we focused a lot in remediation hydraulics, and probably over-focused to some extent, is the dispersivity argument. It still haunts us. There's a lot of our simplified models that are founded on the advection dispersion equation. There are mathematical flaws to that, and observation tells us that transverse dispersivity is always extremely low wherever it's been carefully measured, but it persists. We spent a lot of time trying to knock it down in the book, and probably the more sensible pathway was just to do what John Cherry does, and he says, okay, it's a process that may have some effect, but it's a very, very tiny marginal effect, so we really don't need to worry about it. And when it's carefully measured, transverse dispersivity is in the same range, same magnitude as aqueous phase diffusion. And if that doesn't kill it, nothing will. So what we do find, though, is that we have at least the perception of longitudinal dispersivity, which is really French for heterogeneous advection. Our monitoring wells, particularly long screen wells, are seeing many different pathways go through the well. And so we perceive it if we're sampling a long screen well, and 5 feet may be a long screen in some formations. We see multiple peaks come through that merge into one long tailing curve, and we call it a dispersive aquifer, high longitudinal dispersivity. And what you can see here, this is a three-dimensional model that we built off the raw data set from the Cape Cod tracer studies. And they had, oops, here I'm defeating myself. They had about 630 wells, a highly resolved picture of the distribution of a tracer that was injected in a heterogeneous anisotropic formation. And what you see here is the tracers running at different velocities at different locations in the vertical profile. And so if you're sitting at the end of this with a long well, you start seeing tracer arrive at this point, and the last of it goes through when this part of the plume goes through, and you say this is a longitudinally highly dispersive aquifer. Well, I suppose, but it would be more useful to think about it as a family of velocities, each of them relatively low dispersivity, but when you look at it in a longer screen, you're going to perceive it as a highly dispersive situation. So going into the more highly resolved pictures of our sites allows us to also abandon the notion of longitudinal dispersivity and substitute it as heterogeneous advection. So those Cape Cod tracer studies, by the way, there were 3 injection wells, 656 multi-level samplers over 200-meter flow path. And that transverse horizontal dispersivity, 1.8 centimeters, that is of the same scale as aqueous phase diffusion. The vertical, likewise, 1.5 millimeters, in the same range as aqueous phase diffusion over those distances. So field research, wherever people have closely looked at plumes where they had a single source, they tend to get very long, narrow plumes, very little dispersivity. So again, we focused a lot in the book on trying to defeat this notion, mathematically defeat the notion of dispersivity. And what we should do instead is just focus on what all of the studies are telling us. Transverse dispersivity is extremely low, and we'll just leave it at that. But it has a bearing on how we search for plumes and how we treat them once we get tied into them. This is data from an actual field site in Michigan, which I'm going to come back to in a little bit. One of the big implications of the fact that aquifers tend to concentrate flow in a relatively small portion of the cross-section is that, as a rule of thumb, I'll call it in this case, 90% of the mass transport is occurring in about 10% of the cross-section. And this is a vertical cross-section, transverse cross-section, 30 meters deep and 400 meters across. And you can see this is about a half mile from a concentrated source. And you can see that we've got a couple different lobes here that are running on slightly more permeable zones and an additional plume off to the side. This is actually a different source, as it turns out. But this means, from a remedial perspective, if we put the effort into locating where the transport is occurring, this is where you get the savings on the remedy side for the increased effort in characterizing the transport processes and contaminant distributions. So one of the other things that we did in remediation hydraulics that we'll be revising for the upcoming edition is we originally talked about the transmissive zone or the high K zone, and we originally said immobile porosity. We called it the mobile porosity and the immobile porosity, and that unfortunately tied it in everybody's mind, tied our thinking in everybody's mind to the dual domain models. And that really was not correct. So among other things, people point out, well, porosity can't be mobile, it's not moving. So okay, I got it. But the more important issue is that we're really talking about highly transmissive and somewhat less transmissive zones can cause a distribution of contaminants in the way that we're talking about here. So Beth Parker at University of Guelph points out that roughly 100-fold difference in the hydraulic conductivity will give you contrast that cause transport to be in the higher K zone and storage to occur in the lower. When you think about it, driving down the road, you're going 70 or 80 miles an hour. A person walking on the side of the road looks like they're standing still, right? So if you've got 100-fold contrast in velocities, it makes sense that the high K portion is going to look like it's flying along, and there are opportunities for diffusion to move contaminants into the lower K zones, and then you're into possibly having adsorption or absorption going on, but it's going to be mediated by diffusion in and out of that zone. So the back diffusion issue is not simply a sand over clay issue. We believe, and I'm going to show you evidence, we believe the diffusion, forward diffusion and back diffusion is affecting us even where our contrast is between a 10 to the minus 2 centimeter per second and a 10 to the minus 4 centimeter per second sand, okay? So, and we've got data that's fairly convincing that way. So it's high K versus lower K, not the old dual domain mobile immobile. And one of the ways that we can reinforce that is we took the data from the Borden site and looked, there's almost a 4 order of magnitude variation in hydraulic conductivity in the Borden aquifer that's so highly studied. Everybody talks about it, oh, it's a sandbox. Well, I don't know, we should just assume there's no such thing as just a sandbox, because the sandbox has what, to the geologist handling a split spoon, are subtle variations in sorting. The particle sizes look similar, but the sorting is really having a huge impact. And so we're seeing a 4 order magnitude variation of velocities, and this is where they actually measured the permeability in the lab on samples that were collected at 5 centimeter intervals. The geologist is saying it's just a sandbox, but the lab is telling us something very different. So this is a simulated tracer study and showing the variation in velocities that are going to occur in this sandbox. So here's a real site. This is one of the first sites where we tackled a very large plume that had no investigation done on it before we got there, with the exception of a few monitoring wells near the source zone. And the monitoring wells had really not picked up any 100 ppb kind of concentrations that were picked up in the monitoring wells. And the site owner thought that doesn't ring true, knowing the site history where they had sand bottom lagoons. And the site owner believed that there probably had been some DNAPL released here, but it wasn't showing up in conventional monitoring wells. And the off-site property was city-owned, a cemetery actually, and the site owner wanted to be sure that there was nothing transgressing the neighboring property before literally closing the site. So they engaged us, and we came in, and oh my God, we found that there were very high concentrations where the conventional monitoring wells had found 100 ppb, we found 10 ppm, 10,000 ppb, but, and this was critical, all of the source mass that had originally hit the ground here and come out from the base of the lagoon had apparently washed away over time. The lagoon had been shut down in 1975. It had a RECRA, scooped out and removed. So the original source mass was removed, and there was, let's see, 1975. We started investigating in about 2005. So what are we looking at? 2005, almost 2010. So we had over 30 years of washout. And the upper part of this formation is extremely high hydraulic conductivity. There's some zones in this that are near full centimeter per second hydraulic conductivity. There's an underlying basal clay, a lacustrine clay. But what we found was that we get about a quarter mile off site and we're finding high concentrations, but they're in the lower K zone. It's not clay, but it's silty sand and fine sands where we're finding the highest concentration immediately adjacent to very high K transport channels. Up above, we don't have that lower K material. So what it turns out here is we're looking at the echo of a plume that must have had very high concentrations over a very long distance historically, but washed out. And this is the essentially the diffusion trail. This is the snail trail that got lodged in a lower permeability zone that's about 80 feet below ground surface with 5 feet of clean aquifer between that and the underlying clay. So this is not a clay back diffusion issue. We also calculated whether it could have gotten here by heterogeneous advection. Is this stuff just slow crawling and everything else fast crawled or ran out of the site? And we think the answer is no, because we would have to have started releasing the TCE here back in like the year 2000, I'm sorry, the year 1910 or so. So that ain't working either. So what it looks like is we're getting a redistribution from the high K pathway into the lower K zone. Has to be by diffusion, or possibly if there have been some vertical gradients driving it in, which is another possibility, but unlikely with only a 5-foot sand zone between that and the underlying clay. So we did hydraulic tool profiling. This is a full vertical profile, getting down. Let's see, I'm trying to remember if this starts at the water table or not, but we're getting some interbedded zones down here before we get into the underlying till. We zoomed in on this and took some additional samples, and we've got vertical aquifer profile samples that are collected along here on these dots, and that superimposing here the general geologic setting. I'm going to zoom in on this zone that's carrying all the contaminant down at the bottom. And this track here, the diamonds, is the percent fine grain sediment. And we're only getting up to about, it's less than 20% fine grain. So this is not a clay. It's probably about 10 to the minus 4, maybe low 10 to the minus 3 centimeter per second. It's just that this stuff up above is extreme high hydraulic conductivity, some of it, like I mentioned, pushing up toward a centimeter per second. But look at where the TCE is. It's in the interbedded zone where we've got slightly more silt and finer and slower velocities, but it appears to us that we had in the past, we had a very high concentration source plowing through this area, diffusing into this zone, and this is the remnant that today, when we look at the equilibrium, it's back diffusing out of this zone into the fast-flowing zone above and supporting about 100 ppb concentration from a concentration down in here that's over a ppm. In some areas, it's over 10 ppm. So anyway, what we're realizing is the back diffusion question is not only a clay sand question, it's a higher versus lower K question, and the contrast of 100 or more based on Beth Parker, and we think that holds true here. Contrast of 100 or more means that you're into that territory, but this is a solvable problem because we can induce vertical migrate. We can start driving the flow of water or reagents vertically through this zone and make some progress, actually to drive this stuff out because it's not a massive clay body. But our suggestion is we be looking for this type of scenario in our sites, particularly our large plume sites where we're running over long distances. So I can't overemphasize the significance of sorting. I think, Rick, for your Battelle talk, you say leave your USCS classification at the door. Leave it at school, wherever you learned it. It belongs in the dustbin. We really need to be guiding our field geologists to be recording the percent sand, silts, clays, and so forth so that we can reconstruct the type of reconstructions that Rick is doing and not just have them write down ML or CL or whatever. And if we're actually getting data afresh, we really want to be doing sieve analysis to get as good a quantification on this as we can. So it's not simply the grain size, but the sorting has, I'll say, as much impact on the hydraulic conductivity as the dominant grain size does. So for the future, we want to figure out how to make use of highly resolved models. One of the things that we're doing, and I think this is a suggestion that has been in the literature for a while, and that's to develop type specimens or type classifications from our aquifers. And what we're going to be doing, or we are in the process of doing, is fiddling with highly resolved models over little synthetic test domains to look at the behaviors of different classifications of aquifer matrix. In this classification scheme here we're talking about is going from bulk low permeability to bulk low with a small conductive parting, ranging all the way up to very high permeability with extreme high permeability partings. How is contaminant transport going to behave in each of those scenarios? So that when we look at a hydrostratigraphic analysis, a sequence stratigraphy that tells us we ought to be expecting sort of a moderate permeability with partings of high K, how is the contaminant going to behave in that, and how should we be tracking it and remediating it? So this is for the future, but we think it's a good way to go. So we've got 3 characterization strategies that I think Rick talked about, and I was too ambitious in my timing. Getting plumes to closure. We have to respect the matrix structure, the chemical properties. They're going to control how easily we get there. For small plumes, we can brute force them. For large plumes, it's going to take finesse. That's what that all says. So, think sorting, think storage, and think heterogeneous advection, and you can't go wrong.